Hello and welcome to ChemWonders. Today we're going to talk about the aromatic substitution reactions. The electrophilic substitution reactions on aromatic rings are pretty much common. So we are going to discuss the aromatic electrophilic substitution reactions in this session. Aromatic electrophilic substitution reactions mean the replacement of a hydrogen atom from an aromatic ring with the help of an electrophile. You already know that an electrophile is an electron deficient species and it will always look for reaction with any electron rich center. It may be neutral or it may be a negatively charged center. Aromatic rings generally are electron rich, and that is why they can easily react with an electrophile. And for this reason, the aromatic electrophilic substitution reactions are pretty much common than the nucleophilic substitution reactions on aromatic ring. And above that, the substitution of an electron donating group on the aromatic ring further enhances its reactivity. So let's see how the general reaction of an aromatic electrophilic substitution proceeds. So we have this benzene ring. It's an aromatic ring and it reacts with an electrophile. The electrophile usually has a positive charge or it may be neutral but electron deficient. But in this case, we have mentioned it with a positive charge. So what it does is that it reacts with the aromatic ring through the pi electrons of the aromatic ring, and as you can see here that a proton or a hydrogen ion has been replaced by the electrophile and it gets attached to one of the carbon atoms on the aromatic ring. Let's see the general mechanism for this electrophilic substitution reaction on benzene ring. See, the pi electrons present inside the ring are labile and they can easily react with any electron deficient species. So the two pi electrons from the benzene ring, they attack the electrophile, forming this sigma complex. And as you can see, here we have a positive charge created, which is in conjugation with the two double bonds still present in the ring. So these pi electrons from the adjacent carbon-carbon double bond, they are shifted to help this ring get rid of the positive charge. But what it does is that it brings a positive charge on this carbon atom, which is then shared by the pi electrons from this carbon-carbon double bond, and a new carbon-carbon double bond is formed here, shifting the positive charge here. And finally, this proton is released, it is abstracted by a base, and the aromaticity is restored, leaving this aromatic ring substituted with the electrophile. This is the general mechanism of an aromatic electrophilic substitution reaction. Now let's see some examples of such type of reactions. The first and very common important reaction on aromatic ring is the nitration reaction. In this reaction, benzene reacts with a nitrating mixture, which is a mixture of two strong acids, that is nitric acid and sulfuric acid, and as a result we have a substituted benzene ring on which the NO2 group or the nitro group has been attached to one of the carbon atoms. So the product of this reaction is nitrobenzene. Sulfuric acid is regenerated at the end, which means that it acts as a catalyst here, and water molecule is also released as a byproduct. Nitration of benzene is usually carried out at 60 degrees centigrade in the presence of nitric acid and sulfuric acid. The temperature is kept at 60 degrees centigrade and it is not allowed to rise so as to avoid multi-substitution. Let's see the mechanism of nitration of benzene. The first step in the mechanism is the reaction between the two acids in the nitrating mixture. Sulfuric acid, being the strongest or the stronger of the two, acts as an acid and it donates a proton to the nitric acid, forming this protonated nitric acid, and a bisulfate anion is released in the solution. As you can see here, this oxygen is positively charged, so it can leave in the form of a water molecule, leaving behind a nitronium ion, which acts as an electrophile in this reaction. This electrophile is then attacked by the pi electrons from benzene ring, forming this sigma complex. And as I discussed in the previous slide, in the general mechanism of aromatic electrophilic substitution reaction, this positive charge that is created inside the ring can delocalize over the whole ring, and finally the bisulfate anion that was produced in the first step then abstracts the proton, forming sulfuric acid and restoring aromaticity inside the ring. And we have the product, which is known as the nitrobenzene. Another important electrophilic substitution reaction of benzene is that of sulfonation. Sulfonation of benzene occurs in the presence of oleum, that is a mixture of sulfur trioxide and sulfuric acid, and we have benzene sulfonic acid as a product. Sulfuric acid again is regenerated at the end. Let's see a general mechanism of sulfonation reaction. So again, in the first step, the sulfur trioxide, which is present in the mixture, abstracts a proton from sulfuric acid, leaving behind a bisulfate anion. And you can see here a protonated sulfur trioxide is obtained, which has a positive charge now on the sulfur atom. So this species then acts as an electrophile, and in the next step is attacked by the pi electrons from the benzene ring. So the pi electrons attack the sulfur atom, which of course is positively charged, and as a result this sulfur oxygen double bond is disturbed, and the pi electrons between the sulfur and oxygen, they are shifted towards oxygen, so producing a negative charge on this oxygen atom. And again, as a result, we have the formation of this sigma complex. Again, we have a positive charge inside the ring that is delocalized with the pi electrons inside the ring, and it delocalizes over the whole ring. Finally, the bisulfate anion that was produced in the first step abstracts this proton and restores aromaticity inside the ring. Benzene sulfonic acid is then released as the final product. You can see here that sulfuric acid is regenerated at the end, which means that it again acts as a catalyst just for activating sulfur trioxide, and finally then it acts as a sulfonium ion or as an electrophile in this aromatic electrophilic substitution reactions. So these were a couple of examples of aromatic electrophilic substitution reaction. We'll discuss some more examples in the upcoming sessions. So stay tuned, and thank you so much for watching.